In the last lecture, we have discussed the polarization and polarizability. In this lecture, we will discuss types of polarizability and its significance. The student will be able to learn various types like electronic polarization, Arnold polarization, rotational polarization, and the polarizability associated with these. As we know that polarizability is the property of materials. We'll be able to learn about polarizability and its types. This will give you a complete spectrum of types of polarizability and can have your own opinion on how the polarizability works and what are the significance of this. We have two types of molecules, polar molecules and non-polar molecules. Yes, of course we are talking about dielectric molecules. Dielectric molecules, as we have already discussed in the previous lectures, and the meaning of this di here. This di means two. Those molecules in which the dielectric behavior is there. It means it consists of positive as well as negative charge. As in conductor, there is no accumulation of charge, but in dielectric, there is accumulation of charge. The reason is bound charges, presence of bound charges. Free electrons are not free. If the electrons are not free, then they will behave differently. This develops the dielectric property. Now, I have written here two words, polar and non-polar. Polar molecules means which have permanent dipole moment. There are certain materials which already have dipole moment. If the material is having their own dipole moment, then those materials are called polar molecules, like H2O. Hydrogen molecules have their polar behavior, already have some dipole moment. But on the other hand, some materials are also exist in which there is no dipole moment, but it gives the dielectric behavior only in presence of electric field. So we have defined these polar molecules like H2O are those materials which gives a dielectric behavior only in which have the dipole moment, permanent dipole moment due to their particular specific behavior of electronegativity and positivity in H between H and O and gives special behavior. However, in the case of non-polar molecules, the molecules give the behavior only in presence of electric field. An example of dipole molecule is H2O molecule. The dipole moment of 2H bond OH bond add vertically to give non-vanishing at dipole moment. As in a H2O molecule, like this, behave like this. There is a particular angle between this H2O molecule, and due to this angle between these two bonds, it behaves as having some permanent dipole moment. There are certain molecules on the other hand which are not having any permanent dipole moment, like CO2. In CO2, it behaves like this. A common example of CO2 molecule in the moments of CO bonds. The two CO bonds cancel each other because of the rectilinear shape of the molecule. Here shape is very important, and this results in zero net dipole moment even in the absence of electric field. Polarizability determines the dynamical response of bound system to external field and provide insight into molecular internal structure. In solid, polarizability is defined as dipole moment per unit volume. It gives the idea how effectively uh, the material can be polarized. Using study of polarizability, we can get the various information about molecules. This polarizability is defined as dipole moment per unit volume, and this is denoted by alpha. We define the polarizability, and the unit of polarizability is Coulomb meter square volt inverse, or ampere square second to the power 4 per kg. In CGS, we can also write like centimeter cube. Usually it expressed in CGS unit as a so-called polarizability volume, centimeter cube. Sometimes expressed a to the power minus 24 centimeter cube like this. One can convert SI unit to CGS, which is shown here. Suppose you are having alpha in centimeter square, then this can be done as here to 6 upon 4 pi epsilon 0 alpha, and you can put these values here. So you will get the answer in here. Alpha 0 Epsilon 0 is called vacuum permittivity. The value of this permittivity is 8.854 × 12 FM. If the polarizable volume is denoted by alpha prime, the relation can also be expressed in SI as 4 pi epsilon 0 alpha prime is equal to alpha. We have different types of polarizability in dielectrics, and this is defined as electronic polarization, ionic polarization, and orientation polarization. And finally, we will discuss total electric polarization. There is a relation given by Clausius-Mossotti. We will discuss this relation in a separate video, but we must recognize this, and the polarizability of individual particle is related with electrical susceptibility, and this can be done using Clausius-Mossotti relation, which is a very important relation which gives the idea of neighbors or other states in bound nanoparticles and dielectrics and how it behaves. The polarizability for anisotropic or non-spherical media cannot be generally be represented as scalar quantity. The quantity is vector. Non-spherical media means the properties are not same in all the directions, and this is also termed as anisotropic. And for these materials, a scalar quantity cannot be used. We can define alpha as a scalar implies both the electric fields can only induce polarization component, and xyz direction equal to same way through applied electric field. For example, an electric field in x direction can only be produced x component in V. If that same electric field were applied in y direction, the induced polarization would be same in y component. So many crystalline materials have direction that are easier to polarize than others. Yes, this property is termed as anisotropic property. The crystals have a particular direction in which they can easily polarize. In other direction, they cannot. So crystals are also termed as anisotropic material. The same thing happens with non-spherical bodies. Some molecules and materials with this sort of anisotropic behavior are often optically active, exhibiting effects such as birefringence of light. I think you may be aware of optically active. Optically active means it gives some separation in the case of light. Whenever we apply light, it will separate out, also called polarization. And these materials are also called useful for birefringence. Birefringence means here it has two directions, violates the Snell's law, and we have two ordinary ray and extraordinary ray whenever light passes through this. Here we have shown the polarizability of non-polar molecules. In the first case, the material is spherical. Yes, and it is also non-polar. So there is no electric field exists, no dipole moment exists. But when we put this in uh, field, field can be expressed by this. Then since if the field action is this will be plus and this will be minus. So the electrons of this shell will move towards this, attract towards the plate. If they move towards the plate, then here you will left with positive. And the extent of polarization is determined by its polarizability alpha. Here we have again shown this. In the absence of any field, the center of positive charge, this, and center of negative charge, this, both are coincide each other. But on placing the field, they will be separate out. The electron polarization occurs due to displacement of center of negatively charged electron cloud related to positive nucleus of an atom by electric field. When an external field is applied, like placing the dielectric material between the two plates, the positively charged nucleus is attracted towards the negative side of the electric field, and negatively charged electron cloud is shifted towards the positive, and it behaves as polarized, which is unpolarized or non-polar in absence of these fields. The electronic, we have three types of polarizability as we have discussed in the previous slide: electronic polarizability, ionic polarizability, and orientational polarizability. The electronic polarizability is the relative tendency of the charge distribution, like electron cloud of an atom or molecule, to be distorted from their original shape. And this distortion is called electronic polarization if it is due to electrons, as we have discussed in the previous slide. This may be happen with the electrons. That is why we keep uh, electric field and apply there. The polarizability is defined as alpha in isotropic medium. And this is defined as ratio of induced dipole moment of an atom to electric field. that produce dipole moment. We can calculate induced dipole moment. Monoatomic gases exhibit this kind of polarization, as the monoatomic gases don't have permanent dipole moment. Electronic polarizability is proportional to volume of atom and independent of the temperature. It's not dependent on temperature, it depends only on volume. Now we will discuss another kind of polarization, that is called ionic polarization. In ionic polarization, this occurs due to relative displacement between positive and negative ion. In the first case, which is present everywhere, electronic polarization, in which electron shifts. But in ionic polarization, ion moves. Of course, the ion polarization can also contribute to electronic, because all the ions are made up of the atoms which have electrons and nucleus. So the relative displacement between positive and negative may cause ionic polarization. In the ionic polarization, a crystal or molecule consists of atoms of more than one kind. The distribution of charge around an atom in the crystal or molecule may be positive, may be negative. As a result, when lattice vibration or molecular vibration induce relative displacement of atoms, the center of positive and negative charge got disturbed, and it's called ionic polarization. As it is shown in the figure, that if there is no electric field, this is a ionic substance, NaCl. But when we keep this in electric field, this will be separated out. The location of these centers are affected by presence of displacement. When the centers do not correspond, polarization arises in molecules. The displacement of here, displacement is independent of temperature. In this figure, all three types of polarization discussed. One is electronic polarization that we have shown. Second one is ionic polarization. In presence of electric field, it has some attraction and give you a dipole behavior. And third one is oriented polarization, whenever we have permanent dipole moment. The dielectric polarization in permanent dipoles is represented by these figures. Whenever there is no applied field, they are in random directions. But when we apply field, they try to rotate in the given direction. So the materials which are having permanent dipole moment give orientation. This is different than ionic and electronic, where we observe stretching. So there are two ways stretching and orientation is possible. This occurs in polar substance, which shows dipole moment in the absence of external electric field. And due to random motion, the net moment is zero. But when material is placed in external field, dipole rotates, and this excess of symmetry and aligned with the field. And this is called ionic polarizability to orientation in permanent dipoles. The relative magnitude of the contribution varies in material to material. In non-polar components, the main contribution comes from electronic part and ionic part. Whereas in dipolar materials which are having dipolar momentum, dipole, then the greatest contribution comes from dipolar part. Dipolar part is represented by rotation, whereas electronic and ionic represented by stretching behavior. If they are ionic dielectrics, then main contribution comes from ionic parts. So overall, we have three types of contribution, and some is more in specific and another is more in other specific material. It depends on material to material. In the case of water, for example, the main contribution is from dipolar part. However, the molecules of contains hydrogen and oxygen, so electronic contribution also there. Similarly, we can work out for other examples. The dielectric materials are classified into different groups based on their mode of polarization. If the material fills all type of polarization, then the total polarizability is called alpha, which is equal to alpha I plus alpha E plus alpha O. Is called total polarizability. And here alpha I is the contribution due to electronic ionic polarization, alpha E the contribution due to electronic polarization, and alpha O contribution due to orientation polarization, which is in polar molecules. Yes, one contribution may be more, may be less, depends on materials. In some, alpha I is more, in some, alpha O is more, or alpha E is more. So, we can conclude then we have two types of molecules, polar and non-polar, and we have two types of contribution, stretching and rotational. And in stretching, we have two types of contribution, ionic and electronic. Here, I have shown a matrix for polarizability tensor. As I have discussed in the beginning, then the polarizability tensor is there when there is no preferred direction. If the if moving in, suppose the three-dimension options are there and the anisotropic media is there, so the polarizability is given by this tensor alpha xx, alpha xy, alpha xz, alpha yx, alpha yz, alpha zx, alpha z, where x, y, z are the directions in which the polarization occurs. The element describing the response parallel to applied electric field are those along the diagonal. A large value of alpha yz here means that electric field applied in the x direction and strongly polarize the material in y direction is the meaning. And by the same way we can apply for others. Explicit expression for alpha have been given for homogeneous anisotropic elliptical bodies here. So whenever there is asked in the exam, it can be used for a polarizability tensor. It's a mix of scalar and vector quantity that were termed as polarizability tensor. Thank you. In this lecture, we have learned types of polarizations and total polarizability and possibility of polar and non-polar behavior. Thank you.